welcome. Got it. So welcome to the CPPC seminars. And today we're very honored to be joined by Isabel Oldengott. Isabel started her studies in Aachen, where she did her undergraduate degree and completed a master's under none other than Yvonne Wong. And then she went on to get her doctorate at University of Bielefeld with Dominik Schwarz. And then from that point onwards, held postdoc positions at the University of Bielefeld, and then University of Valencia, and then now currently at the University of Louvain. And today she'll be telling us about cosmic QCD epoch at large Lepton flavor asymmetries. The floor is yours.
Yeah, thanks a lot for the invitation. So I will talk about this work that is based on these three papers here in collaboration with colleagues in Bielefeld and also Heidelberg. So does it still look okay for you? Okay, I somehow have to. So if you can't see the slides properly, tell me, because for me, everything just got a bit shifted. I'm pretty sure you're very familiar with this kind of plot about the cosmic evolution of our universe. The standard model, cosmological standard model we believe in today is based on the so-called hot Big Bang theory, which is confirmed by measurements of the Hubble diagram, mainly confirmed by the measurements of the Hubble diagram, this cosmic microwave background, and primordial element abundances. So we today have a pretty good understanding about the epoch of recombination and the EV scale when the first neutral atoms formed. We have a very good understanding as well about the formation of the first nuclei in the MeV to keV range, called Big Bang nucleosynthesis. So this epoch, Big Bang nucleosynthesis, is also the earliest epoch we can probe at the moment. But of course, before this, there's also a lot of interesting physics going on. We have the QCD. There are at least two epochs where possible phase transitions could occur. There is the QCD epoch at roughly 150 MeV, where quarks and gluons confined into hadrons, and the electroweak epoch at roughly 100 GeV, where gauge bosons and fermions became massive particles. So both of these epochs somehow leave an imprint on the gravitational wave spectrum. If they are first order transitions, then they would in general lead to the emission of gravitational waves itself by processes like bubble collisions also. If they are simply smooth events, crossovers, then the equation of state during this process still leaves a characteristic imprint on the gravitational wave spectrum of inflation. So therefore, the new era of gravitational wave measurements gives us some hope to obtain insight about these very early epochs. According to the standard model, both of these transitions are expected to be smooth events, crossovers. However, there are many possible scenarios that would lead to a first order electroweak transitions. But with much, as far as I know, much less mechanisms that would indeed induce a first order QCD transition. And this is exactly what I will focus on during the rest of this talk. So when we talk about the QCD epoch, it's very important to keep in mind this so-called QCD diagram. So the QCD diagram is usually displayed in the plane of temperature and baryon chemical potential. One has to say, if your system has other conserved charges, for example, electric charge, then it's not just a 2D plot, but it's a multidimensional plot. So for every conserved charge, you add another axis to your phase diagram. This QCD diagram charts at which baryon chemical potential and temperature baryonic matter exists in the form of a quark-gluon plasma or in the form of a hadron gas. We know from calculations of Lattice QCD that at very low baryon chemical potential, this transition between the quark-gluon plasma and hadrons is a crossover event. And we believe from effective models of QCD that at large baryon chemical potential and low temperature, it's a first order transition. And this leads to the speculation that there should somewhere exist a critical endpoint, which marks the point above which, so to the right of this plot here, you would have if your system crosses the line here at the solid line here, you would have a first order transition, and if your system crosses the dashed line here, it would simply be a smooth crossover. Our universe follows a certain path in this diagram, and the standard, what I call standard trajectory. So this path in the QCD diagram is called cosmic trajectory, and the standard trajectory somewhere starts here at large temperature and low chemical potential, and then the universe cools down and it passes as it passes through small chemical potential. That's why we believe that the cosmic transition is simply a crossover, and then at low temperatures it approaches the value of the nucleon mass. So this cosmic standard trajectory is based on the assumption that the universe has a lepton asymmetry that is roughly as large as the baryon asymmetry. But it has been shown in 2009 by Stuke and Schwarz that if you add a lepton asymmetry, if you let the lepton asymmetry be larger than the baryon asymmetry, you would shift the cosmic trajectory towards larger values of the baryon asymmetry. So this is basically a spoiler already for the rest of the talk. This is exactly the mechanism that I will try to explain in a bit. Since this work in 2009, we have improved the method how to calculate this cosmic trajectory quite a bit. Our universe, as you can see here, is pretty well measured. The error bar is pretty small, but actually the order of magnitude here, 10 to the minus 11, is poorly understood. So 10 to the minus 11 is a very tiny number, but actually it's much bigger than what is expected from the standard model of particle physics. And therefore the big question is, why is this tiny little number so big? And this question gives rise to a whole research band of theories of baryogenesis and leptogenesis. And the idea behind leptogenesis is to create a lepton asymmetry that is then transferred into a baryon asymmetry by so-called swallowing processes. And this directly leads to the standard assumption that the lepton asymmetry is roughly as large as the baryon asymmetry, which means it's a tiny number. Are there possible caveats to this whole picture? First of all, we should keep in mind that swallow-on processes are experimentally not confirmed. They have a very large energy, which makes it pretty hard to test this whole picture. Then, for some reason, it could be that swallow-on processes are simply suppressed in the early universe, which somehow also destroys this whole picture of the lepton asymmetry being as large as the baryon asymmetry. Or it could be that a large lepton asymmetry only gets created at later times when swallow-on processes are already inefficient. In any way, I'm really not an expert of theories how to create a large lepton asymmetry, but for me, the bottom line here is that lepton asymmetry is certainly one of the key parameters to understand the origin of the matter-antimatter asymmetry of the universe. So what do we know about the lepton asymmetry? It really makes sense to assume that we are living in a charged neutral universe, which means that the lepton asymmetry in the charged lepton sector, so in electrons today, must entirely compensate the baryon asymmetry, which means that the charged lepton asymmetry today is very small. That means if there is a large lepton asymmetry, it would be entirely carried by the neutrinos, which means that it could be hidden in the cosmic neutrino background. And I say hidden here because, as you know, those relic neutrinos have a very low energy, and that makes a direct detection of them at the moment impossible. do we nevertheless have any constraints on the value of the lepton asymmetry? Yes, we have, from the cosmic microwave background and Big Bang nucleosynthesis. And therefore, let's take a look at the definition of lepton asymmetry. So lepton asymmetry is defined as a sum over the different lepton flavor asymmetries. So indeed, we do not only have one lepton asymmetries, but we have a lepton asymmetry for each flavor. And now, you can express this lepton asymmetry as the net number density of neutrinos. So the number density of neutrinos minus the number density of antineutrinos divided by the photon number density. And actually, this equality is only true at late times. At early times, the lepton asymmetry would really appear in the charged lepton sector and in the neutrino sector. I will talk about this later a bit. There are two different definitions around for the lepton asymmetry. The one is here dividing by dividing through the number density of photons. This one has the kind of disadvantage that, for example, during positron-electron annihilation, the lepton asymmetry is not constant as photons get heated up, but neutrinos not, and therefore it's changing in this epoch. The alternative definition is dividing by the entropy density here, and this is really a conserved quantity. And I will be kind of sloppy. Sometimes I use the definition of the lepton asymmetry by that one, and sometimes the other one with the entropy density. In both definitions, you can simply assume a Fermi-Dirac distribution for neutrinos, including chemical potentials, and then you see that the lepton asymmetry depends linearly, and there is also qubit dependence on the chemical potentials of neutrinos. So in other words, large neutrino chemical potentials imply a large lepton asymmetry. In order to see what how we can obtain observational constraints, let's also look at other what chemical potentials change in the evolution of the universe. So neutrino chemical potentials lead to an enhanced relativistic energy density. And this is as usually parameterized by this number n effective, the number of relativistic degrees of freedom. And we see here that n effective is kind of blind to the neutrino flavor. So it's degenerate in the three different neutrino flavors. And it's also insensitive to the sign of the lepton asymmetry. So whether we have a negative or a positive lepton asymmetry always leads to an enhanced n effective, to an enhancement in the expansion rate of the universe. On top of this, we also have another effect. Neutrino chemical potentials also directly lead to modified, directly impact the weak interaction rates that in turn set the neutron to proton ratio at the onset of Big Bang nucleosynthesis. And the kind of change that you get is, you can see in this formula here. So that impact, that effect, the impact on the neutron to proton ratio is really only depending on the electron neutrino chemical potential. So this is really an effect that, at least in principle, is flavor sensitive. Both of these effects, the enhanced and effective and the modified weak interactions, have a direct impact on the abundances of primordial elements. So in this plot here, I'm showing the abundances of helium, deuterium, tritium, and lithium-7 as a function of the lepton asymmetry. And I'm assuming here equal chemical potentials for the three different flavors. I will comment on this assumption in a bit. And now you can obtain constraints on the lepton asymmetry by directly measuring these primordial element abundances. There is also another way. Both of these things, N effective and the helium abundance, also directly impact CMB anisotropies, and therefore you can also obtain constraints on the lepton asymmetries from the cosmic microwave background. So in general, the constraints from BBN, from primordial element abundances, are somewhat stronger than the one from the CMB. But then on the other hand, there's still systematic uncertainties in BBN codes, so different BBN codes giving you slightly different answers for especially the deuterium abundance. And there are also discrepant measurements of the helium abundance, and therefore, at least in my opinion, when it comes to lepton asymmetry, BBN and CMB are somewhat competitive when it comes to these constraints. And the constraints on the lepton asymmetry are both roughly in the range of 10 to the minus 2. So if we compare this to the constraints that we have on the baryon asymmetry, one can say that actually those are very weak constraints in a sense that they still allow a lepton asymmetry that is something like 9 orders of magnitude larger than the baryon asymmetry. There's also another loophole. So besides those constraints being in general pretty weak, both the CMB and BBN is only sensitive to the total asymmetry and not to the individual lepton flavor asymmetries. That was shown in these works here. And maybe at first it sounds like a contradiction, because I was just emphasizing on the slide before that the effect on the neutron to proton ratio only depends on the electron flavor. However, what happens in reality is that roughly at 10 MeV, neutrino oscillations become efficient. And they lead to an equilibration of the individual lepton flavor asymmetries. That means that even though before 10 MeV, you can have, if you start with very different initial lepton flavor asymmetries, after BBN, after neutrino oscillations, they all have a value that is roughly 1/3 of the total lepton flavor, total lepton asymmetry. And that means that individual lepton flavor asymmetries before 10 MeV are almost unconstrained. They still have to, of course, the sum of them still has to fulfill the BMB and CMB requirements. But for example, if they are very large but have opposite signs, they can compensate each other, and such a scenario is basically unconstrained. So for the rest of the talk, I will just take an entirely agnostic point of view and simply treat lepton asymmetries as entirely free parameters for cosmology. So now let's talk. Let's go back to the calculation of the cosmic trajectory and how to compute it. So if you want to compute this cosmic trajectory, you simply apply the conservation laws that are valid before the onset of neutrino oscillations at 10 MeV and below some new physics scale where a lepton asymmetry gets created. So I'm just calling it TBSM here, and I don't really care about the creation mechanism. Yeah, and at this temperature regime, you have the conservation of lepton number, baryon number, and electric charge. And these conservation laws are written down here. So L alpha, B, and Q are the asymmetries. S is the entropy density on the right-hand side. N are the net number densities, so already particle minus antiparticle. Yeah, and for the lepton number conservation, of course, we have 3 equations here for the 3 different flavors. Each of the conserved charges can be associated with a chemical potential. So we also have 5 chemical potentials: the baryon chemical potential, the charge chemical potentials, and the leptochemical potentials. And on the right-hand side here, we have a sum over all the contributing particle species. So for example, for the baryon number, you sum up all particles that are around at that epoch carrying a baryon number of B1 here. And then by assuming chemical equilibrium, you have relations between the individual particle, chemical potentials of the individual particle species. And most importantly, you can relate those individual chemical potentials to the chemical potentials of the conserved charges by these equations here. So just, yeah, and now it makes sense to assume again that our universe is charge neutral. So you can set Q equal to 0. This is a known quantity. The baryon number can also be fixed to what we know from the cosmic microwave background. And that means our only free parameters are the Lepton flavor and the asymmetries that I will treat as free input parameters in the following. So just to sum up, we have 3 input parameters. We have 5 equations with 5 variables, the chemical potentials of the conserved charges. And if you solve this set of equations for different temperatures, you obtain the so-called cosmic trajectory. Just a small intermezzo, because this often leads to a lot of confusion and isn't clear to many people in the beginning that why there is a connection, a relation between the lepton isometries and the baryon chemical potential. So if you have a large lepton flavor asymmetry, L alpha here, then in principle you induce also a large asymmetry in the leptonic in the charged lepton sector. So you induce a large electron isometry, for example. But on the other hand, you have Q equal to 0, you have a charge neutral universe, which means that if you have a large electron isometry here, you somehow have to compensate this electron isometry in the quark sector. So you induce large chemical potentials for the quarks. And now if you just look at the relation of the baryon chemical potential as a function of the quark chemical potentials, you see directly that if you induce large quark chemical potentials, you also obtain a large baryon chemical potential. So this is more or less how the whole mechanism works. Yeah, going now back to the question how to actually compute this cosmic trajectory. It makes sense to split up the contributions from leptons and the ones from baryons, because the leptonic sector at these temperatures is super easy. We are here talking about temperatures around 150 MeV, where weak interaction processes are super efficient. So you can assume for the leptons that they really have a perfect Fermi-Dirac distribution, including chemical potentials. The complicated part is really from the baryons, because here you have strong interactions effect, and that's where it becomes complicated, because QCD effects are just not easy to deal with. And yeah, in the following, I will introduce 2 different methods that we used in order to describe the thermodynamic quantities for the baryons. Yeah, so the first method is something I worked on with people in Bielefeld. And in that method, we apply results from Lattice QCD. So the idea here is to split up the cosmic trajectory into 3 different temperature regimes. At high temperatures, we can kind of neglect the strong interaction effects and simply assume that we have an ideal quark gas, which basically means we assume equilibrium distributions for the quarks. Okay, at low temperatures, it's easy again. We can just neglect the strong interaction effects, and there we simply assume what is called a hadron resonance gas model. So we simply assume that the hadrons as well have equilibrium distributions. The complicated part is, of course, at temperatures around the QC, close to the QCD transition. Yeah, as I said before, here we use results from Lattice QCD. However, unfortunately, Lattice QCD is kind of restricted to be exact only for zero chemical potential because of what they call the sign problem. And what they usually do in order to also access regions of non-vanishing chemical potentials is to Taylor expand the QCD pressure. And if you do so, then you'll see that the first order contribution, so there is a zero order contribution, the first order contribution vanished, and you have a second order contribution, and this second order contribution is then parameterized by these chi here, and these chi function is called are called lattice QCD susceptibilities. So these susceptibilities can be calculated on a lattice, and all the thermodynamic quantities we're interested in, also like the net number density, can be expressed through this lattice QCD susceptibilities. So we simply use this, but of course I have to say here the Taylor expansion somewhat restricts the applicability of these QCD susceptibilities to relatively small chemical potentials. I will later comment on this a bit more. And now I'm just showing you the results. Here are some plots just for the case of equal lepton flavor asymmetries. So again, here the trajectory in the plane of temperature and varying chemical potential. This one also shows the trajectories in the plane of temperature and charged chemical potential. And I'm showing here the trajectories for increasing values of the total lepton isometry. We have here the high energy regime, the ideal quark gas, the low energy regime, the hadron resonance gas. And in between, we use the lattice susceptibilities, and we use two different data sets that are available. One is based on only taking into account the UD and S quark, and the other ones, the triangular one here, also takes into account the charm quark. So first of all, what this plot shows is that indeed, if you enhance the lepton isometry, you shift the trajectory towards larger values of the baryon chemical potential. The green curve here is the standard trajectory. I think especially for that one, you see that everything really smoothly fits. If you go to larger values, then you see that the lattice the susceptibilities using only the U, D, and S quark, they do not really converge smoothly to the high, to the ideal quark burst, to the high temperature regime. Which tells us that you really have to take into account the charm quark in order to smoothly connect the different phases here. Now I'm also showing you a plot for a case of unequal lepton flavor asymmetries. So as I pointed out before, this case of unequal lepton flavor asymmetries is basically unconstrained, therefore it's also not a big surprise that the blue curves here for the unequal case lead to in principle allow larger values of the baryon chemical potentials than the one of equal lepton flavor asymmetry. So that's the green line here, because simply the green line here has the CMB and BVN constraints that it has to fulfill. So in principle, we could go to larger values than the lepton flavor asymmetries that I chose here for the blue lines, but there are some restrictions to our methods. The first one comes directly from the reliability from the Taylor expansion. So it's clear that at some point, if you go to larger and larger chemical potentials, the Taylor expansion just cannot be reliable anymore. And we try to quantify this so this plot somehow in the PDF version looks a bit crappy. I think you can't really read what is written in the shaded regions here. So that orange, the lighter orange shaded region here is the region where the second order contribution to the QCD pressure becomes larger than roughly 10% of the zero order contribution. So we just said, like, if this happens, then our method is probably not very reliable anymore. And yeah, the other constraints comes from the formation of a pion condensate. So this is more easy to understand if you look into the trajectories in the mu-q plane. So in the hadron resonance gas approach, the charge chemical potential is directly given by the pion chemical potential. In general, if the chemical potential of a boson becomes larger than its rest mass, then you will come into a phase of a Bose-Einstein condensate. And this is exactly what happens here. If we go to larger and larger lepton asymmetries, at some point, the pion chemical potential becomes larger than its rest mass. And for our method, that simply means that yeah, our hadron resonance gas approach doesn't work properly anymore because the pion number dense thermodynamic quantities, they start to diverge. So we have to do something different here. And yeah, for us, it's really just a restriction to our hadron resonance gas approach. However, this pion condensate can also have cosmological consequences that I'm not going to discuss here, but have been yeah, discussed in this paper here. Yeah, it turns out that the restriction from the reliability from the Taylor expansion is stronger than the restriction from the formation of a pion condensate. Yeah, so this method, I would say, is really nice if you only care about relatively small lepton asymmetries. But of course, this method cannot be used in order to give an answer to the question whether large lepton flavor asymmetries can induce a first order cosmic Q transition or not. So in order to answer that question, I started collaboration with a postdoc in Heidelberg, Fei Gao, who's an expert on functional QCD methods. And Fei and his colleagues, they so in functional QCD, you derive thermodynamic quantities by solving Dyson-Schwinger equations. And these Dyson-Schwinger equations, they are a set of in principle infinite number of coupled equations, and therefore you somehow have to truncate these equations. And Fei and his colleagues in this 2015 work, they used something they call the rainbow ladder truncation. And within this truncation scheme, they calculated, as you can see here, the number density of the U and the D quark as a function of the chemical potential. So here, yeah, the different lines are for decreasing temperature values. And what you can see here is that somewhere between the red and the black line, you suddenly see this appearance of the step-like feature. And this discontinuity has been interpreted as the appearance of a critical endpoint and identified to this value here. Of course, one has to say that probably this is not the end of the story. The whole, this critical endpoint depends somewhat on the truncation scheme that is used. Yeah, we really thought of this whole method in that context here of the cosmic trajectory more as a proof of principle and not maybe as a tool to get a precise computation of this cosmic trajectory. So yeah, we used these thermodynamic quantities derived from the Dyson-Schwinger equations and implemented them into our calculation of the cosmic trajectory. And I'm here showing you the cosmic trajectory for one specific case here. So LE is equal to 0 in that scenario here, and L mu and L tau have opposite sign, such that the CNB and BBN requirements are always fulfilled. And in this plot here, you see the cosmic trajectories again in T mu B for increasing absolute values of the lepton flavor asymmetry. And you see that somewhere between the green and the red curve, suddenly this kink appears. If you look at the number density, so same values here, you see that for small temperatures, at small temperatures here, you suddenly observe this spike-like feature. And yeah, this continuity that happens somewhere between 0.06 and 0.07 can be interpreted as a first order transition. So here we really demonstrated that indeed lepton flavor asymmetries do not only have an impact on the cosmic trajectories, but they can really induce a first order QCD transition. Yeah, now we also studied, so that was just one realization. We studied several, I would say, benchmark models of lepton flavor asymmetries. And yeah, the one in red here, scenario 2 is just the one I showed you the plots of. And the other scenarios 3 to 7, they are all constructed in a way that they always fulfill the CMB and BBN requirements. The first one is a scenario of equal lepton flavor asymmetries. And yeah, you can really make predictions when those scenarios for which values of the lepton flavor asymmetries you would find a first order transition. And yeah, maybe it's worth to mention that the first one, the one of equal lepton flavor asymmetries, this would require a total lepton asymmetry that is larger than roughly 10 to the minus 1. And that's already excluded by the CMB and BBN constraints. So yeah, this simply shows that in case of equally distributed lepton flavor asymmetries, we can already exclude the appearance of a first order cosmic QCD transition. The other scenarios of unequal lepton flavor asymmetries, they are all having solutions, so they are all able to really induce a first order cosmic QCD transition. Yeah, now a comparison between the two different methods. Here I'm just focusing on the first case of equal lepton flavor asymmetries. The solid lines here are the one using the results from functional QCD, and the dashed lines are from the other method. And I would say that here, at least at very high temperatures, there is, yeah, the two methods I would say are pretty consistent. There is no big difference here at large temperatures. So here it works quite well. Yeah, if we go to the intermediate regime around the QCD transition, I would say, yeah, there is not really a good match between the results using Lattice QCD, so these are the dots here, and the one from functional QCD. But at least the trend is the same. So both of these lines, they bend into the same direction. If we go to low temperatures, then yeah, I think we just have to admit that there is really not a good match between the two different approaches. And yeah, our interpretation of this discrepancy here is that especially in that region around the QCD transition, probably the lattice results are the more reliable because the functional QCD method, it really depends on the truncation scheme that is used. However, at lower temperatures, I think one could also argue that the hadron resonance gas is maybe not the best description because at least at temperatures around 150 MeV, strong interactions and effects matter, and they probably would also alter that these dashed lines here a bit. Yeah, so let me just summarize and conclude. Yeah, so I wanted to convince you that lepton flavor asymmetries before 10 MeV roughly are almost unconstrained, and they have an impact on the cosmic trajectory during the QCD epoch. I introduced two different methods in order to calculate the cosmic trajectory. One makes use of lattice QCD susceptibilities, and the other one uses results from functional QCD. I would say that for small values of the lepton asymmetry, method 1 is probably more reliable. So if you're, for example, interested in the equation of state, including lepton asymmetries during that epoch, and you don't care whether there is a first order transition or not. If you're happy to restrict relatively small lepton asymmetries, then method 1 is probably the method of choice. However, method 1 simply doesn't allow to give an answer to the question whether there can be first order transition. And this is why I think method 2 is actually the only possibility that we have in order to study this effect. And yeah, indeed, method 2 revealed for the first time that that there can be a first order cosmic QCD transition if the lepton flavor asymmetries are unequal. If they are equal, then in principle, if you make the total lepton asymmetry large enough, there can be a cosmic QCD transition, but this is already excluded by CMB and BBN constraints. So that's basically what I wanted to tell you.
Great, thank you for the talk, Isabel. Yes, so anyone have any questions? Maybe give it a minute to digest what just happened.
Can I just ask? Oh, hey, Isabel. Very nice talk. Can I ask one quick question about those Schwinger-Dyson approaches with those truncations?
Oh no.
It's probably more for your collaborator than for you. I know.
Exactly, that's the part of questions I'm scared of. Okay, but
yeah. No, I'm having just. I'm wondering. Did your collaborators consider there are multiple different truncations? So can you basically go a little bit one order more and then one order less? And does it then agree better? Or does it tend towards the lattice result or not? That's
a good question. We actually want to look at this. So Faye at the moment, so apparently I really don't know a lot about functional QCD, but apparently there are 2 different ways around something with the sum approach that I just talked about using these Dyson-Schwinger equations. And then there is also an approach, functional renormalization group. And apparently this other approach that Faye is working on now is considered to be more reliable. So they also find a critical endpoint that is somewhat different from this Dyson-Schwinger approach. And right now, I'm waiting for Faye to give me his data set to see if with this other method we find a better consistency with the lattice approach. But especially about this truncation scheme, at least Faye didn't change the truncation scheme. I'm not sure what others did in that field, but it seems like people more believe in the functional renormalization group approach.
Okay, good. Yeah, interesting. Now with those truncations, it's right. You don't have control over what's going on. That's why I was asking. Yeah.
True.
Thanks. I will unfortunately have to run because I have to teach, but yeah. So thanks again for the talk.
Okay, don't be shy. Speak up if you have a question.
Yeah. Hey. Could you maybe go back to the beginning of the talk where you show us the QCD phase diagram for the first time?
Yes. Yeah, maybe that one.
Yeah, right. Maybe I missed that, but I'm just wondering. So we see that this red line just goes down, and then it has this kink at, what is that, 45 MeV or so?
Yeah.
Well, what exactly happens at that temperature? So
I mean, yeah, you can just show that at some point the trajectory just entirely gets insensitive to the value of the lepton asymmetry, and you just approach this nucleon mass, which also makes sense because the chemical potential at low temperatures simply, it's the energy that you have to put into your system in order to create a baryon. And at low temperatures, where baryons are non-relativistic, you just, in order to create a baryon, you simply have to create the energy of the mass. So that's why they all approach the nucleon mass here. When this turnover exactly happens, if I remember correctly, this is, yeah, I think this is when pions annihilate,
Right.
or decay. So I think this is more or less where this transition happens.
Okay. All right, thanks.
I also have a question around this part of the talk. So when you said the lepton asymmetry only adds positive contribution to the N effective, I didn't quite, that wasn't very obvious to me. Can you explain why is it only positive?
Yes. I will just go back to, so here you see on that formula of the definition of the lepton asymmetry, if you have a negative chemical potential, you have a negative lepton asymmetry, right? If you have a positive one, you have a positive lepton asymmetry. In N effective, there's just a quadratic and a quartic dependence on the chemical potential. So whether you take a negative or a positive chemical potential, which is the same as saying whether you take a negative or positive lepton isometry, both will lead to an enhanced N effective and never to a decrease.
Right, but physically, so does that mean if you want to create an asymmetry, you have to always add more particles rather than having some process that just shifts from the particle to the antiparticle population? Because then wouldn't that keep the relatively species like number density the same?
No, yeah, apparently not. I mean, I don't know if I can find a better.
It just means that if you have a negative asymmetry, it just means you have more antiparticles. And it doesn't matter whether you have more antiparticles or more particles, you're still contributing relativistic energy density. That's all.
Right, but I mean, if you get more antiparticles, what if you took that from the particles and have some process that just?
So the thing is that you don't. The point is that you're agnostic about where it comes from. So it could be negative for you know.
Oh, okay.
Yeah.
But also, I might have missed this, but how do you get away with saying if you have more lepton asymmetry, how do you stop that from converting to a very large baryon asymmetry?
Yeah, so I really didn't talk about it a lot, but I'm just assuming that the lepton asymmetry gets created after these follow-on processes are efficient, and then you don't have this transfer of the one thing into another. Or I assume that for some reason there are no follow-on processes, and then the initial lepton asymmetry is just a free parameter.
I see. Okay.
Yeah.
Thanks. Okay. Anybody else have questions? If not, I actually have one more question. Sorry. So the Lattice QCD part, is that something that you're doing with Dominic as well, as are you taking just from some other group's results?
No, I cannot do lattice. We took it from collaborators in Bielefeld because there is a pretty strong lattice group in Bielefeld. Yeah, we simply took their results.
Okay, I was wondering like how hard would it be to get the second order, the next order term, so then you can, I don't know how much that freedom allows you. Maybe you can push the larger asymmetries, but maybe the computation cost will be too much.
Yeah, seems to be pretty hard. At least we are asking them already since 2 years or so to get better data than this. But so far, I mean, since 2 years, they say like, yes, you will get them, you will get them. But yeah, seems to be pretty hard.
That's fair enough.
Yeah.
I think Lattice QCD is like the poster child for numerical problems that are too hard.
Yeah, they have their own cluster, and yeah.
Okay, so if no more questions, then let's thank Isabel again for this fantastic talk, and do it.